Okay, let's talk about estimating a population mean. A little bit of review of terminology. A parameter is some kind of a numerical summary that has to do with the whole population. For example, the population mean. A statistic, on the other hand, is a number that represents a sample. So perhaps the sample mean. So usually we do not have access to the population. The only thing we have access to is a sample. And so our only option is to use the sample to estimate the value for the population. So a point estimate is the value of a statistic, which comes from the sample that estimates the value of a parameter that comes from the population. And it's easy to remember that because the population and the parameter both begin with P, and the statistic and the sample both begin with S. Okay, so if we are using a sample to represent a population and we take the average, the mean of all the data points in the sample, we would not necessarily expect it to match the population mean exactly. In fact, it would be rather surprising if it did. What we want to do is quantify how close would we expect it to be. So, this brings us to what we call a confidence interval. A confidence interval for an unknown parameter is an interval of numbers that is created by a point estimate for the parameter. Remember, the point estimate comes from the sample. The confidence level, which we usually write as a percentage, represents how confident we are that that confidence interval happens to contain our population parameter. If we have a population and over we randomly choose a large number of samples of whatever size, all the samples are the same size, and for each of those samples we calculate a separate point estimate, and simplest one is this point estimate, the sample mean, and for each of those sample means we create a confidence interval. Then if we are talking about a 95% confidence level, that means 95% of all those confidence intervals are going to contain the population parameter. Once in a while, you will get a fluky sample that's got a bunch of outliers or something in it, and so it ends up not containing the population parameter. So the 95% confidence is really a way of expressing our confidence in the algorithm that generates the confidence intervals. So how do we get the confidence interval? We start with the point estimate of our parameter, and then we put a margin of error on either side. So basically, we take the point estimate, and then we add and subtract the margin of error. And that is true no matter what we are estimating, whether we're estimating the population mean, the population proportion, the population standard deviation. Same approach. We always take the point estimate, add and subtract the margin of error. Okay, so point estimates for the mean and the standard deviation. Not surprisingly, the point estimate of the population mean, mu, remember, is the sample mean, x bar. And the point estimate of the population standard deviation, sigma, just to review our Greek letters, is the sample standard deviation, S. Remember, the Greek letters are used for population parameters. So for every sample, the sample mean will always be right in the center of the confidence interval. If we use E to indicate the margin of error, then our confidence interval is x bar plus or minus E, and we can write it in interval notation. Okay. Let's look at an example. Suppose we have a confidence interval that's already been created, So we're sort of doing this one backwards just to show you the general layout of how this is going to work. Okay, so here's a number line. Here is the number 125, so 0 is off to the left somewhere off the page. Here is, 138. This is a 95% confidence interval. Where is my sample mean going to be? My sample mean is going to be right smack in the middle. This is my sample mean. Okay. To get our sample mean, we average the two endpoints. That will always give you the point that's halfway in between them. So we're going to take the 125, add the 138, divide by how many we have, so we divide by 2. And that is going to give me 131.5. Another way you could think of this is you could take the width. The width is going to be what? 138 minus 125, which is 13. And so then my margin of error is going to be half the width. Which is going to be 13 over 2, so 6.5. So in other words, if I measure from here to here, this distance is 6.5, and then this distance is also 6.5. I know my drawing's not perfectly to scale, but you get the idea. And this is my E, my margin of error. Okay, so my sample mean we've already found, and my margin of error as well. So let's write that down. Remember, X bar is always the correct notation for your sample mean. There's not really an official notation for margin of error. Lots of times people use E, but E gets used for other things as well. So I'm just going to put 6.5. So, and notice if you do 125 plus 6.5, that gets you right to the 131.5. Let me label that on my picture. Okay. I want to remind you of something else here. The standard deviation of the sampling distribution of the sample means. Okay, what is the sampling distribution of the sample means? That's the set of all possible sample means from all the possible different samples of a certain fixed size. Okay, that is calculated by taking the population standard deviation and dividing it by the square root of the sample size. So remember our margin of error on each side of X bar, and I lost a bar, is going to be the same. And so we basically, instead of writing the margin of error as just E, we turn that margin of error into some multiple of the standard error. Okay, so what I'm calling here is Z. That stands for Z critical. Remember, the Z-score is the number of standard deviations away from the mean. And so if we're following a normal distribution, if you remember, we worried about Z-scores, and we figured out the area when we had quantities that were normally distributed. So that Z, that critical value of Z, is a multiplier that tells us how many standard deviations are on each side of that sample mean. Okay, so a little bit of reminder here. So Z alpha, here's an alpha. Z alpha is the positive z-score, so the area to the right is alpha. So for example, if I had some kind of a curve, if this was my z alpha here, then that means this area over here, this area is equal to alpha. Okay, and then often we end up having to cut the alpha in two. Same idea, the subscript is going to be the critical value so that the area to the right is that same alpha over 2. Okay, let's go back to something we've talked about before. Remember our empirical rule? So remember this applies for bell-shaped distributions. If you'll recall, about 95% of the observations or data points will lie within 2 standard deviations of the mean. So now let's talk about a more exact value of this. If the alpha is 0.05, so notice this 95%, what is that as a decimal? 0.95. If we add that to the alpha equals 0.05, that gets us to 1. So whenever we know the confidence level is a percentage, we also know the alpha. Okay, so the critical value of Z is Z alpha over 2, which is 1.96. So let's draw a little picture here. So if my alpha is 0.05, that is the same as the confidence level is 95%. Okay, but confidence levels are normally done as percentages, and the alphas are done as decimals. Okay, so let's sketch ourselves a little normal curve. Okay, so right in the middle of this, and let's make this a standard normal curve, which means that the mean is 0, and the values on the x-axis are z-scores. So, come over here to the right. This area right here is going to be alpha over 2. So what we're going to do is we're going to take that 0.05, divide it by 2. You should need a calculator for this one. What's that going to give us? 0.025. Okay, so we're going to cut it in half. Okay, over on the other half of the alpha goes on this end. So over here, we are also going to have alpha over 2. So we put half of our alpha in each end. So if we look at this curve, let me label it a little better here. This area right here is going to be 0.95. Okay. So let me mark my x-axis here. So this is the critical value of Z, right here where the color changes. So this is Z 0.025 on this side. It's a positive number. And then, of course, over here on the left, our critical value is a negative number. They're going to be opposites. One will be positive, one will be negative. Okay, so that is our standard normal curve. Let me get some more space here. Okay. Now, what about our curve that's on the same scale as our original variable? So this is another curve, not on the same scale. So right here in the middle, this is going to be the mu, the population mean of all the possible x bars. Okay, and so then on this end, and this end, what we want to do is we want to still put alpha over 2 in each end. Remember, the area under the whole curve is always 1 for any of these normal curves. Okay, and so then right here, this is, instead of being a z-score, it's going to be that ux bar plus my z times my standard error, which I'm going to write as this. That just means the standard deviation of all the x bars. Over on this side, it's going to be the same idea, the mu of all the x bars minus the critical z-score multiplied by the sigma of all the x bars. So it looks like that. Okay, so now we need to figure out what the z.025 is. So we're going to look up in our normal table Okay, so we want to go to our normal table, and depending on what kind of a normal table you have, there's different ways it can be done. Okay, let's look at this one. Okay, so the way that book that I'm currently using in this class lays out their table is like this. Okay, so it gives always the area to the left. Some normal tables, instead of giving the area to the left, will give the area between the z-score and the mean. In other words, they'll give this little area right here. So some tables will give me that. Not the one I'm using here, so I'm going to get rid of that. But if you happen to be using a table like that, you probably already know how to look that up. Okay, so these are the ones for the negative z-scores. Now I'm going to move down to the ones with the positive z-scores. Okay, so if you're using the other kind of table, the one that goes from the z-score over to the mean, you only need one page to do your table. But we've got a two-page table here. Okay, so I'm just bringing this up to remind you what our table looks like. So now I'm going to go back to where we were. We need to figure out the area to the left. Okay, so the area to the left, if we go all the way here, so the area to the left of that positive critical value is what? 0.975. How did I get that? I got that by taking 1, because remember the whole area under the curve is 1. I'm going to take 1 minus that 0.025. And that's going to give me 0.975. So now what I'm going to do, I'm going to look up area equals 0.975. I'm going to look that up in my normal table. And what we want to do is figure out the z-score for that. Okay, so let me go back to my table. Okay, so we want to look up area equals 0.975. Okay, so we want here, these are the positive, these are the areas that are larger than 0.5 here. So let's see if we can find, so we're not looking down the left and right edges here. we are looking in the body of the table. Okay, so 0.975, where is that? I think I see it. It is right here. Do y'all see that? Okay, so then we follow it over to see what our z-score is. And it's going to be, I go up here, that's 0.06. This is 1.9. And so I add those together, and that gives me what? 1.96, right? Okay, so let's go back. I'm just erasing those so they won't be in our way when we come back to this table later. So that corresponding z-score is z, and this will be, I'm going to label this z.025 is equal to 1.96. This is an extremely important number. Okay, so if you go back to your empirical rule, where it said, let's look at this piece, about 95% of the observations will lie within 2 standard deviations of the mean. So it is really 1.96 standard deviations of the mean, from the mean. This should say, no, actually, that's okay, never mind. My grammar reader got a little carried away. So when we say about 95%, it's a rule of thumb. So 95% is easy to remember. And we say about within 2 standard deviations of the mean. So we want exactly 95%. Then we're going to be within 1.96 standard deviations of the mean, which is really close to 2.